Okay, I want to do two more examples of limits of functions. First one is we're going to show that x squared goes to 4 as x goes to 2. Okay. So let's start out, and we're going to let epsilon be bigger than 0. So now we have to figure out what delta would be. So let me just draw a little picture over here. Got x squared, and we're focused in here at 4. Okay. And I want to be in this little epsilon band around 4. So zoom in a little bit. My delta band has to be a little bit smaller this time, right? And we're at 2. So delta in each direction. So I can't just take epsilon to be delta this time. Alright. And if epsilon's really big, then I sort of have to worry about like curvature down here. It starts going back up again, and it kind of gets a little bit messy. So our approach to figure out what delta is going to be has to change a little bit. Okay. So let's just do a little bit of algebra. So we want that if 0 is less than x minus 2 is less than delta, that x squared minus 4 is going to be less than epsilon. Okay, so let's focus on this equation a little bit, the thing that we want to have happen. I can factor that. I can factor it as x minus 2 times x plus 2 is less than epsilon. And that's good because this piece right here we've already got a bound for, right? And then this other piece we have to figure out how we're going to make that stay sort of small. So this gets big if I'm far away from 0, right? Or far away from -2 actually. But if x gets big, this blue piece gets big. So we're going to have to say that we're going to stay close enough to 2 in the first place that this thing doesn't get big. So we're going to take delta and we're going to define it in two parts. We're going to take delta to be the minimum of 1, so we have to stay close to positive 2. We can't go to the left of 2 very far or to the right of 2 very far. That in our picture, it guarantees that we're going to stay in this bound no matter how big we choose epsilon to be. Even if we take this epsilon bound to be really big, we don't care because our we don't really care because our delta bound is still just going to be at least this small, right? We're not going to go outside of this little vertical red band unless ever. We don't have to. We might make it smaller. We might bring it into the little green band if we need to, but that's only if the epsilon we pick is small enough to require us to. So we're going to take the minimum of 1 and this other function that we're going to determine later. And I know that it's going to be epsilon divided by some constant. We're going to figure out what that constant's going to be here in a second. Okay, so let's look at this equation again. I've got x minus 2 times the absolute value of x plus 2. And I want to keep this thing small. This piece is going to be less than delta no matter what I do, right? Because that's by definition what we're going to set less than delta. This piece over here, it could get big, but since I have this minimum of 1 here, it can't get too big. I'm not going outside of a distance of 1 from 2. So this piece here, this is going to be at most 5. Because if I'm a distance of 1 from 2, I could get all the way up to 3, or I could get all the way down to 1. So this piece is going to be between, right, between 3 and 5. So the biggest that I could multiply my delta by would be 5. So over here what I'm going to do is I'm going to take epsilon over 5 and put it there. Okay. So let's finish the proof using that idea. So we let epsilon be greater than 0. Set delta equal to the minimum of 1 and epsilon over 5. Okay. If we do that, then if 0 is less than x minus 2 is less than delta, we get that x squared minus 4 is equal to x minus 2 times x plus 2, right, is less than or equal, strictly less than delta, because of the first part, times 5. Because we know that delta is at most 1, that means this number can be at most 5. Right? Okay. And now, this is also less than or equal to epsilon over 5 times 5, and this inequality is because delta is at most epsilon over 5. Okay, could be 1, which might be smaller than epsilon over 5, but it's at most epsilon over 5. And then we get that that's less than epsilon. So we've used this string of inequalities. X squared minus 4 is less than epsilon. Okay, which proves that limit. Okay, the next one I want to do will be similar. Oops. Let's prove that the limit 1 over x as x approaches 1 equals 1. Okay, so the other one I had an exponential function, so I had a function that wasn't just, hey, x equals y. It wasn't linear. It wasn't quite as easy for us to figure out what delta had to be. Here I've got a reciprocal function. It's not going to be quite as easy for us to figure out what delta will be. We're going to use that same technique, that same idea, that delta can be the minimum of two numbers. And the first number is going to kind of give us a bound on how far away from 1 I can get. And then once I'm in that little region around 1, I can use some more algebraic math to figure out, okay, in terms of epsilon, now that I'm close to where I'm supposed to be, what should my delta really be? Okay. So let's do this again. Some scratch work over here. We've got absolute value of x minus 1 less than delta and bigger than 0. And then we want to get to absolute value of 1 over x minus 1 is less than epsilon. Okay, so let's work with this equation again. I get x minus 1 in absolute value times 1 over x in absolute value if I do just a little bit of algebra. And I want that to be less than epsilon. This piece again is really good for us. It doesn't ever get too small. This piece is less than delta. And this piece is the one that we have to put a bound on. Well, that piece can get really, really big if I'm close to 0. So I want to be closer to 1 than 0. So let's make a minimum of, say, 1/2. Need this far from 0 to get a bound on it. Okay, so let's take delta equal to the minimum of 1/2, and we'll get some multiple of epsilon again, and we don't know what that multiple is yet, but we'll fill that in a second. Okay, so if I do that, then my expression, absolute value of x minus 1 times the absolute value of 1 over x, well, this is going to be smaller than delta, and this piece, it gets bigger the smaller x is. And the smallest x can be, if delta is 1/2, has to be within 1/2 of 1, so the smallest it can be is 1/2. So this piece is at most 2. Okay? And then that lets us figure out we want this to be less than epsilon, so delta should be less than epsilon over 2. So, yeah, delta should be less than epsilon over 2. Okay, so let's now go up here and prove this. So let epsilon be bigger than 0. Take delta equal to the minimum of 1/2 and epsilon over 2. Then if 0 is less than the absolute value of x minus 1 is less than epsilon, we get absolute value of 1 over x minus 1 is equal to the absolute value of 1 minus x times 1 over x is less than delta times 2, and that 2 comes from, since x is between 1/2 and 3/2, this guy can be at most 2, and that's also less than or equal to epsilon over 2 times 2, and this is because we chose delta to be the minimum of epsilon over 2 and 1/2, and that's equal to epsilon. So putting that together, we get 1 over x minus 1 in absolute value is less than epsilon, which is what we wanted to prove.